Welcome to Module 3, Calculus for AI. 15 videos. By the end, you will understand exactly why your loss goes down when you run gradient descent, why the chain rule is the entire mechanism of backpropagation, and why certain activations cause training to stall. It starts here, with limits. When PyTorch computes loss backward, it is computing a limit, the instantaneous rate of change of loss with respect to every parameter. Every gradient is a limit. Every weight update is a limit. And every convergence guarantee is a statement about what happens as a limit approaches infinity. Today, formal definition of limits, epsilon-delta, continuity, and 4 places they appear in training. The limit of f, x, as x approaches a equals L means, for every positive epsilon, there exists a positive delta such that if x is within delta of a but not equal to a, then f, x, is within epsilon of L. This is the epsilon-delta definition. It makes arbitrarily close mathematically precise. One-sided limits approach from the left only or the right only. The full limit exists if and only if both one-sided limits exist and agree. The 5 limit laws: limit of a sum is the sum of limits, product is product, quotient is quotient provided denominator limit is non-zero, and so on. L'Hopital's rule handles 0 over 0 and infinity over infinity forms by replacing numerator and denominator with their derivatives. The squeeze theorem: if G is always below F and H always above, and both converge to L, then F must also converge to L. A function f is continuous at a if 3 conditions hold simultaneously. 1. F of A is defined, no hole. 2. The limit of f, x, as x approaches A exists, no jump, no asymptote. 3. The limit equals f, a, they must match. 4 types of discontinuity: removable, where the limit exists but does not equal the function value, patchable with epsilon; jump, where left and right limits disagree, ReLU derivative at 0 is a jump; infinite, where the function diverges, division by 0 before batch norm epsilon; oscillation, where the limit does not exist. Key theorem: differentiable implies continuous, but continuous does not imply differentiable. ReLU is continuous everywhere but not differentiable at 0. The corner creates a jump in the derivative. The intermediate value theorem: a continuous function on a closed interval hits every value in between, the foundation of root finding. 6 key limits. The derivative definition: f prime of x equals the limit as h approaches 0 of f, x plus h, minus f, x, divided by h. Derivative of e to the x is e to the x, proven via this limit. Derivative of lane, x, is 1 over x, giving us the chain rule for cross-entropy loss, hence we write log p plus epsilon, in practice since the limit is infinite at x equals 0. Sigmoid derivative equals sigma x times 1 minus sigma x, maximum 0.25 at x equals 0, vanishing for large magnitude x, the vanishing gradient problem. L'Hopital: limit of sin, x, over x as x approaches 0, both are 0, so apply L'Hopital, cos, x, over 1, equals 1. Euler's number E: limit of 1 plus 1 over n all to the n as n goes to infinity. Softmax temperature: as T goes to 0, softmax becomes Argmax, a continuous interpolation via a limit. 4 applications. 1. Gradient descent. Every loss backward call analytically evaluates the derivative limit for every parameter via the chain rule. The gradient is the exact limit, not an approximation. 2. ReLU subgradient. At x equals 0, left limit is 0, Right limit is 1, they disagree, so the limit does not exist. PyTorch assigns subgradient 0 by convention. Works because measure 0 discontinuities almost never affect SGD. 3. Batch norm epsilon. When variance is 0, all inputs identical, the denominator is 0, creating an infinite limit. Epsilon shifts it away. Adam Optimizer uses the same trick with epsilon in the denominator of the weight update. 4. Learning rate scheduling. Robbins-Monroe. Sum of learning rates equals infinity, so we can reach any basin, and sum of squared learning rates is finite, so we converge within it. Learning rate must approach 0 as a limit. 4 things cold. 1. Epsilon-delta. For every epsilon greater than 0, exists delta greater than 0, such that 0 less than absolute x minus a less than delta implies absolute f, x, minus L less than epsilon. 2. Continuous at a requires f, a, defined, limit exists, they're equal. 3. Differentiable implies continuous, not the converse. 4. F prime equals limit as h goes to 0 of the difference quotient. Exercise 1. Lim, x to 0, sin, x, x, L'Hopital gives cos, 0, equals 1. Verify, np.sin of 1e8 divided by 1e8 should be very close to 1. Exercise 2. Removable discontinuity in x squared minus 4 over x minus 2, factor, cancel, limit is 4. You now understand limits at the epsilon-delta level, not just intuitively. You know what continuity requires and how discontinuities appear in the activations and normalization layers you use every day. Every gradient you have ever computed was a limit, now you see the machinery underneath. Video 19 is derivatives, chain rule, product rule, partial derivatives, and the Jacobian. These are the tools that make backpropagation work. Subscribe so video 19 is ready. Write the limit definition of the derivative in the comments. F prime of x equals lim, h to 0, of f, x plus h, minus f, x, all over h. See you in video 19.